Oh yeah, she's good.
Okay.
Just you know,
I didn't look.
it's a hard trip, you know.
Yeah, the last month sucks.
Okay, so we're recording and play. All right, we're in class 3. This one is called Down the Rabbit Hole. Now, now I just have to come up with titles. I just can't help myself, you know. No, but the reason is we're finally gonna start talking about atoms. You know, class 1 was atoms aren't real. Class 2 was like, look, y'all don't know jack, you know, and we need to just prove some stuff that's not there, you know. Oh, I'd like to give thanks to iStock Video for giving me this clip of an atom, you know. So atoms, what are they? And how did we come to the understanding that our world was comprised of atoms? Where did this come from? John Dalton. We'll start with him because he's like, of course, there's a whole history going up to John Dalton. Actually, atomic theory, and this is funny because everything always goes back to ancient Greece, you know. Yeah. The atomic theory came from, I can never say his name, Epicurus, whatever, I can't say. But he came up with the original atomic theory. That, you know, he was on the beach and he saw the sand, you know, the fine pebbles. He's like, everything, you can keep dividing stuff, but eventually you're going to get to something that's the fundamental piece of that. The problem with his theory, as revolutionary as it was that, you know, it was like a piece of cheese. You know, a piece of cheese, you will get a cheese atom. And a cheese atom was squishy and delicious, you know, or something metal was a solid, hard, like rectangular type atom, you know. Something that was flexible was the atom like had a ball socket joint, you know, so the atom could like flex, you know. But there was an atom for each particular thing. He wasn't trying to see how we saw atoms now, you know. Now, of course, his rival, not his rival, but his contemporary, Aristotle, said, you know, everything's made up of earth, wind, fire, and water. And nobody remembered that atomism until thousands of years later, so. John Dalton, though, was a chemist, and doesn't take a leap of imagination to understand that atoms are key to chemistry. Yeah. He was an English chemist, physicist, and meteorologist. Through his work with gases, he formulated the first modern atomic theory in his work, A New System of Chemical Philosophy. So here's John Dalton's atomic theory. We'll just go over it first. Elements are made of extremely small particles called atoms. Atoms of a given element are identical in size and mass and other properties. So far, he's true. Atoms of different elements differ in size, mass, and other properties. Absolutely true. Oh, here's where we got a little bit off. Cool. Atoms cannot be subdivided, created, nor destroyed. Of course, he got the word atom from the ancient Greeks. And the atom, atomos, means it's indivisible, you know. And for the longest time, atoms were thought to be indivisible. So we found out you can divide them. Yeah. And then those little things, you know, like an electron is an actual indivisible. Yeah. But then the other stuff, they could take those, divide those up some more. So eventually you get atoms. We can call an electron an atom because it is fundamental. But the thing about atoms is the atom is the smallest bit of something that makes it something. You know, like this is aluminum. Aluminum is on the periodic table. It has a certain configuration of electrons, protons, and neutrons. That's what makes it that. Yeah. So just with electrons, protons, and neutrons, you have a specific mixture to make up everything. So that's why they don't call them atoms. Yeah. Atoms of different elements combine in simple whole number ratios to form chemical compounds. And again, we'll see how he deduced these things. But he understood that there's compounds and that atoms form and grow compounds. And Stanislaw, you can sit right here. You know, I'll play with you. So in chemical reactions, atoms are combined, separated, or rearranged. Now remember, chemists have been doing this for centuries. Actually, chemistry, which was previously called alchemy, is one of the oldest forms of science. You know, not just that they were trying to make gold, but yeah, wizards and magicians, and even in ancient Egypt, it's like they understood that chemical reactions and how you can mix stuff and do stuff. And yeah, they wanted to make gold and do this and that. But chemistry or alchemy is one of the oldest forms of science. And now we're trying to finally get to the age where they can understand what is happening. You know, I remember as a kid taking all the household cleaners and mixing them together because I was making a potion. And now that I'm a parent, I'm realizing, where the heck was my adult supervision? Like, seriously.
Yeah.
And one time, and it was in a plastic bowl, I remember, it was a thick plastic bowl.
Oh my
It started to
God.
heat up, and I felt it was getting warm. And then it started bubbling.
What did you do?
And then steam, like these fumes started coming out. I was like, oh my gosh. And then the plastic bowl started to melt.
Oh.
And then this, whatever I mixed up, came out of the plastic onto the gorgeous like tile. Oh my God, my mother killed me.
Eating the time.
Yeah, it didn't eat the tile, but it just totally stained the grout, and it was
Right.
just, it was bad, you know. And how do you clean that up? It's like bubbling, boiling.
You don't, you mix your ground.
Yeah.
Or vinegar on it.
But the point is that scientists are like, how is this happening? What is happening? Because until we can understand what is going on, we can't control it. We can't learn from it. You know? Oh, here's a later rule he added, which I think is really interesting. It's the rule of greatest simplicity, which stated that when atoms combine in only one ratio, it must be presumed to be a binary one unless some cause appear to the contrary. So we'll translate that to English, meaning he assumed the formula for water wasn't H2O, it was just OH, or HO, but I said OH, you know. Or for ammonia, instead of NH3, it was NH. The reason being, well, it says in the next slide, this was merely his assumption based on his belief in the simplicity of nature. And again, this was a totally Christian, religious, God-fearing man who sought to, science wasn't a way to bring down God, it was just to make him understand God's creation. No evidence was available to scientists to determine how many atoms of each element combine to form a compound. So just to get to the point where they understood that water was made up of hydrogen and oxygen, they didn't know the ratios, you know, how many of what, you know, but they were going to get there fairly rapidly. So the atomic concept of the material world really came into being in the form that is taught not only in textbooks, but to most of us 2 centuries later. So 200 years ago, they started to have a good grasp on this. However, this idea only slowly gained favor in the 19th century. So we're going to go over a lot of this, but remember, just because you see something from the past, you're like, oh, he was on. Like the ancient Greek. You know, oh, Thomas, nobody believed him. And it got lost for millennia until it was rediscovered in Persian in the Middle East. And then once we translate, we're like, oh my gosh, he knew about atoms. Well, who would have thought, you know? So there's this guy. He's another famous chemist. Joseph Louis Gay-Lussac. I'm probably saying that wrong, but he established by experiment that when 2 gaseous substances combine together, the volume of one gas is always in simple proportion to the volume of the other. So if the volume produced is also a gas, so if the 2 things combine and are still a gas, they don't turn to a liquid, that volume is a simple proportion. Here's a simple picture. So if he took 3 volumes of hydrogen, now a volume is whatever they had at that time. You know, they understood that I remember the measurement. They had a funny measurement, but whatever. So you take 3 volumes of hydrogen, and then you have 1 volume, you know, it's 1/3 of that, of nitrogen. When you combine them together, you get a new formula, now NH3. But they didn't know that. They just knew it was a simple proportion. It was always like these whole numbers. There was this symmetry they saw, like 4 and 1, you get 3, or 2.5. I mean, there was also, you know, the decimals. But I was going to show a list. I should have left it in there. But slides showing these proportions would give out another proportion that was an equal number. Now, they didn't understand why this was, but it still made them understand that this is how this is made up of this, you know. This is how they started to understand molecules. There's a molecule of nitrogen and hydrogen. And we don't know how they work. We don't know how many they are, but this is how it goes in there. Then there's the law of pressure temperature. The pressure of a gas of fixed mass and fixed volume is directly proportional to the gas's absolute temperature. So this is the key to give scientists an understanding of what heat was. Because what the heck is heat? Like, you heat something up, you heat a piece of metal, it glows hot. Like, what is heat? Well, with gases, they were able to simplify that. Okay, so we know that there's little molecules. So they don't know, but they conjecture, little molecules. And when they heat them up, the pressure mounts.
Right.
So maybe these molecules are moving faster, and that is, since they're hitting the walls harder and harder, that is what the pressure is increased, which is pretty trippy if you think about it, because my son was playing with a balloon like on Wednesday. I was working on the slide. And, balloons are very, but then you blow it up and they hold. So all that's happening is your air molecules are in there with a certain pressure.
Yeah.
That pressure means that there's trillions of, the number is just astronomical, literally. Actually, it's more than that. You say astronomical because there's so many stars in the universe. Atomically, the numbers are even bigger. So you shouldn't even say astronomical. It doesn't do it justice. Because you say there's a billion, trillion stars in our universe. Well, there's a billion, trillion atoms in like a teaspoon, like a sugar cube. It's so astronomical how many atoms we're made up with. Just you. Like the number of atoms in your body are more than all the stars in the universe. And that's an incredible number. And that's just you. Not counting the room and everything else. So the point being is those trillions and trillions of molecules are really ricocheting so hard and fast against that plastic that's what's keeping it up. Of course, these things, again, they deduced these scientifically over and over, and they saw that once you heat something, as many of you know, whether you don't know scientifically, if you take a can of hairspray and throw it in a fire, bad. It's going to explode. Now, why does it explode? Well, you may not know it scientifically, but instinctively, heat's going to make stuff blow up. How many of you had a Coke can blow up in your car? Anyone? Soda can? Just me? Oh, in the freezer. How many in the freezer? Ron, never? No, it was the second summer I was here. It was 117 degrees, Arizona Mills. And as I was going to my car, walking to my car, I heard it. And it was loud. Boom! And I was like, I thought like somebody shot or whatever. And I get in my car and I was like, what's that smell, And then I look at the ceiling of my car and it's all like dark brown. Remember, it was my black Honda.
I remember your black Honda. It was sticky in there and everything.
Yeah, it was sticky and everything. And I'm like, what is that? There was the Coke can. The entire top had busted off. Like, it got so hot, it blew apart. Pressure. Okay. Avogadro. How many have heard of Avogadro?
Yeah.
You remember Avogadro?
No.
Or heard of a mole? Remember in chemistry, a mole? Remember a mole? Okay, a mole is one of the smallest units of like a substance, like gas, right? And it's based on Avogadro's. Oh, I should have put a picture of him. He looks like a little weasel, like a genius little weasel, like his head, So Avogadro's law, and again, I was going to go really into detail, but we don't really need to. It's not that important. But he deduced that basically equal volumes of all gases at the same temperature and pressure have the same number of molecules. So he said it doesn't matter like what it is. It could be different types of things. But at the same pressure, at the same temperature, at the same volume, there's an equal number of these molecules, which he knew were made up of smaller atoms, but they had to deal with the molecules. Experiments today have proved Avogadro's hypothesis to be correct. He did such breathtaking experiments that he actually, this is again 150 years ago, he broke down and actually got a number. Now here, nobody even believed these things exist, except for chemists, but he actually found a number. And now it can be proved that each liter of a gas at the pressure of 1 atmosphere, which is like your standard pressure, at a temperature of 0 degrees centigrade, contains roughly 27 billion molecules. So he was able to work this out. Just the thing about chemists, and this is the thing I love about chemists, is they're seriously like CSI detectives. I mean, they really are. The way they deduce things and they just do reason, it's almost like a clue. Like, I know because, it wasn't Mrs. White, and it wasn't the colonel. Like, just by deduction, they can solve the crime, just by doing this deductive reasoning. And it's really a testament to chemistry and how they're still doing it now, like with DNA and genes. And if you really figure out how they map the gene for something, it's brilliant how they just deduce, and they deduce things down, and they're still not totally sure, so they finally get things right. But it's all like Clue. That's the way I think of it. Stanislaw. Look at that. Not Stanislaw. This guy is, if you're from Italy, he's like Einstein, one of the most famous chemists, and he's really big in Italy. He showed how the atomic weights of elements contained in volatile compounds can be deduced from the molecular weights of those compounds, and how the atomic weights of elements whose compounds the vapor densities are known can be determined from the knowledge of their specific heats. So I don't even know why I wrote that. I should have just wrote it in English. But basically, as they got better and better, so now they know how many molecules are in something, right? And they know how much something weighs. So they started to list out and chart in the early periodic table what the weight of a molecule is.
Right.
And then as they figured out, okay, now I know how much a molecule of water weighs. But now they figured out using Avogadro, that, okay, if I combine 2 things of hydrogen with 1 thing of oxygen and I get 1 thing of water, steam, then you sort of deduce that H2O. Takes 2 hydrogen and 1 oxygen, must make a molecule. Now, they don't know how these molecules attach. They don't know how they stick together and how they talk to each other or whatever. But he was able to take it a step further because now he could, knowing those weights, they were able to deduce, I think it was like 8, one of the main 8 elements, their the actual weight of hydrogen, the actual weight of oxygen. Now, they were off, but they were like within the 90 percentile.
Yeah.
I mean, this is amazing. I don't know. To me, I just find it really amazing, especially.
I never heard of this guy, but that's a cool name. That's my name. My name has an E in front of it.
Exactly.
Yeah.
Stanislao Cannizzaro.
Yeah, I mean Stanley.
So he championed Avogadro's notion that equal volumes of gas at the same pressure and temperature held equal numbers of molecules or atoms, and the notion that equal volumes of gas could be used to calculate atomic weights. In so doing, Cannizzaro provided a new understanding of chemistry. So now chemists were finally starting to get grasp of what's going on. Like, they still had so many gaps to fill, but they were starting to understand like how, boron or how because even back in the day, apothecary, the early pharmacists, they could concoct crazy poisons and all this stuff. And it was all deduced from little chemical reactions, Now, they never knew how these things work, but now they were starting to get a scientific understanding of what it was. Now, it's important to point out that physicists were just like, dude, okay, no such thing as molecules or atoms. You guys, this is just a convenient mathematical trick, is what you hear a lot. And they had different names for this, but this is just a convenience. These aren't real. Now, maybe it's nice for you to break things up into little pieces, but there's no conclusive evidence, because how do you prove an atom? It's very tricky. I mean, here's something that's so small, it's unimaginably small. You cannot imagine how small an atom is. And I had a slide where I had a bunch of analogies, but we'll maybe go over it later, but it's stupid small. Okay, stupid small. Oh, here's one. If you take an atom and blow it up the size of the Earth, right? No, I'm getting it wrong. I don't even want to do it wrong. Skip that. Okay, so now we're going to go to Ludwig Boltzmann. So by the 1890s, many chemists still did not take these ideas seriously. However, it was at this time that the behavior and details of atoms were explained mathematically. Now they were taken more seriously. So now the physicists and the mathematicians were getting involved because the data was becoming so conclusively clear that, again, I skipped it, which I shouldn't have, was when chemists finally started to figure out that things could be isolated. What would make you think that water was just water, right? It's water. What would make you think water was actually broken up into 2 other things that you never saw before? And so the first step for chemists was the fact that purifying and trying to find out what is a pure something, because we know most of everything that we come in contact with is a compound. It's a molecule. It's difficult, at least with liquid substances, to find something pure. Like mercury is the case, and mercury has a lot of weird characteristics. Probably because because of the reason is it's not a compound. So now that the physicists and the mathematicians were getting involved, now everyone's like, okay, we need to look at this a little bit closer. They developed the idea that gas is made up of very many atoms or molecules. Avogadro gives you the idea of how many, which can be thought of as tiny hard spheres that bounce around, colliding with another, and the walls of the container that held the gas. So chemists, again, already understood this. But now the physicists were realizing, okay, well, I can work with this, you know? Remember, Newton's ideas were already hundreds of years old. They understood motion. They understood calculating if you hit a ball at a trajectory. So if you start thinking about, instead of atoms, little billiard balls, and they're all moving around, hitting each other, like, okay, I can do this. Action, reaction, you know, velocities, forces. Okay, we can model this. So this related directly to the idea that heat is a form of motion. So when a gas is heated, the molecules move faster and faster, which increases the pressure on the walls of the container. And if the walls are not fixed in place, the gas will expand.
Yeah.
Now, the key feature of all these ideas was the behavior of gases could be explained using Newton's law of mechanics in a statistical sense. Now, remember, a ball or a whole bunch of little balls we can calculate, but now we have to obviously get into statistics. So there's no way you could track the motion. Now we can with supercomputers, which I covered. But how do you track a trillion collisions all happening? They had to look at a why. They had to look at statistically what's going to happen. How are these things going to move around? Now, any one atom might be moving in any direction of the gas at any time, but the combined effect of many molecules colliding with the walls of the container each produces a steady pressure.
Yeah.
This led to the development of a mathematical description of gas called statistical mechanics. And you hear this word a lot. And usually they'll say statistical in a type of science. And usually they're talking about the mathematical way to formulate really small stuff and what it's doing. So here's Ludwig Boltzmann. He came up with a mathematical formula for the second law of thermodynamics, also known as the law of entropy. So how many heard of the law of entropy? Most of you heard. Any mentorship graduates have heard of it. His famous equation for entropy showed clearly the connection between entropy and probability. So what is entropy, for those of you that don't know? Entropy is the summation of the second law of thermodynamics. What is the second law of thermodynamics? The second law of thermodynamics states that the entropy of an isolated system never decreases because isolated systems always evolve towards thermodynamic equilibrium, and it's a state with maximum entropy. So let's translate that. Oh, I didn't translate it? Okay, I'll translate it on the fly. Basically, it means, think of something ordered. Okay, if you drop it and all those things fall, or now all these things are bouncing, they're chaotic. Maybe they started, maybe the gas was solid, right? It was a solid sphere of hydrogen. And then you heated it, and now the hydrogen's bouncing all over. It tended towards chaos. And this chemists have seen forever. They know that things tend to go towards disorder. Now, why is this a big deal in Christian arenas? And this is one of the few scientific principles you'll hear in Christian arenas, is because this is one of the things people throw at most against evolution. You know, the whole principle of evolution is that the primordial soup, right? That all this just random goopily globbly stuff, and then one day they just combined, like they had order, and they formed a molecule, you know, and then the molecules got together and formed a cell. And the cells got together, and before you know, you had a mitochondria. Things got ordered. Well, there's a problem with that, because one of the fundamental things that we know in science is that it's not how it works. Everything tends towards disorder. Now, once you actually have the DNA, obviously the DNA is the code and structure, like, yeah, you have that order, but there's nothing in science that would point us towards how we got to that, besides a creator, obviously. You know, makes perfect sense. We were designed, whether by God or by aliens, whatever you want to pick. Someone designed us, which is why evolutionary theory is kind of unpopular. I don't know what you call it. What do they call it? Intelligent design. Most scientists are like, oh, aliens made us. Okay, we were designed on quantum computers, you know. And so that's why this is a big deal. Now, I'm about to give you a different view of entropy. So the way we've been using it as Christians is actually a little bit wrong, but that's okay, because what I take away, I'm going to give back to you. So how did Boltzmann's equation change the view of entropy? At first sight, it didn't change it at all, but in fact gave it a mathematical credence. So this is good. Like, even if you weren't sure about entropy, everyone knows math is math. Okay, like, you can argue about theories all day, but 2 plus 2 equals 4. All right? And so as soon as he came up with this math formula that fit what we see in nature, the entropy, the chaos, you would think to say, like, oh my gosh, then this is it. This is absolutely true, which in a sense it was. But the question was, what did the math imply? And you get this a lot, which is really funny. And it's funny because that's what separates us from geniuses, you know. Geniuses think about stuff that most of us are like, what's the square root of 9? Anybody? No. That's half the answer. What's the other half?
Plus or minus.
Exactly. So it's plus or minus. Now, we automatically, we just ignore the minus because whatever. Well, there's a square root, and we'll hear about it later in quantum mechanics. And there's square roots everywhere. Remember, in gravity, we're going to come up everywhere. Something divided by something squared, something square root of something. And it was an energy level, right? And it was a square root. So everyone assumed, okay, energy, we're going to get the smallest number. The smallest was like 0.2. And then there's negative 0.2. Well, this genius, I'm just kind of jumping ahead for a second just to prove a point. He was like, well, the math says plus or minus, And the lowest energy level is the lowest state, in this case, that an electron could be in an atom. It's not 0.2, it's negative 0.2. So he just went crazy. Anyone else would have been like, there's no negative energy level. 0 is no energy. What are you talking about negative energy? Kind of like a black hole, And the whole point was a whole branch of science kind of brought out from this principle that we're just like, plus or minus, no, it's not. Like, who cares about the negative, However, there are many of the older society who balked at the statistical version of entropy despite its success in the laboratory. Okay, so here we have the whole Newton effect. Remember where Newton, I think I discussed it, where when Newton first talked about his theories and how it was determinism. Did I talk about that? How he said the world worked like a clock, and how the religious people were all really against that because they were like, you're basically saying you could be like God. Because that's what determinism means. If you know everything, and if you know that how everything ticks and talks, you're omniscient, you're omnipresent. You could know everything, if you could do it. And now, back then it was like impossible, but just the notion of it happening. Now we have supercomputers, maybe it's possible, but then I told you it's actually impossible because of quantum mechanics. Here was the same thing. So the old school, all the new scientists were accepting this, but the old ones, the Victorian, the Prussian society was like, this is ridiculous. Why is this ridiculous? Deck of cards. Think of entropy like a deck of cards. All right, I'm going to give you an example. You take a perfectly ordered deck of cards and you shuffle them, right? You shuffle them over and over and over. Entropy states that disorder will increase. Now, this is this experiment we can do. You can shuffle the cards all day, and they're just going to get more and more mixed up, right? I've been playing Uno a lot with my kids, and I'm realizing you've got to shuffle really well. If you don't, somebody's going to get 4 wild cards in a row, and it just messes up the whole game. But you really have to shuffle. It only is going to increase. Or does it? That's the question. Or does it? Mathematically speaking, this is not true. Statistically, it is not only possible, but perfectly conceivable that if you shuffle a deck of cards enough times, you will eventually shuffle them back into order. Eventually, you're going to shuffle that deck and look at it, and they're all going to be in perfect order. So mathematically, it can go in either direction. Now, this is a little bit different. Sometimes you can tend to oversimplify this, kind of like the lottery. Like we all know the lottery, it's impossible. But it's not impossible. It's just like really, 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 really very not possible, And you have a 1 in 65 million chance, But the thing is, the chance is there. You really can guess all 6 numbers that are going to roll out of that little ball, This is a little bit different, and I'll explain why. Here's another example. Again, when you drop a large rock on the ground, it hits the ground, right? Gravity, that energy, hits the ground and turns into heat, all right? That heat, just dissipates in the floor and whatever, the ground will just absorb that heat, This is the law of conservation of energy, which I don't know if you guys remember that in school, but energy is neither lost nor destroyed. Okay, so Star Trek, phaser, you're vaporized, you're not really gone, okay? your little pieces are there. It's just little. And people are, if TJ gets vaporized and I walk through TJ, I just breathe them in, TJ's now in me, So, however, what is the likelihood, now think about this, what is the likelihood that the heat in the ground will just happen to, just like the lottery, to reverse direction, order itself, and all shoot in the reverse direction that it went in, and all that heat will then propel the rock upwards into your hand? That's ridiculous. But here's the problem. Mathematically, it can happen. And not that it can happen, it has to be able to happen in order for the math to work out. This is why the guys from the old school were like, dude, this is ridiculous. Yeah, exactly. You must model in reverse as well. And here's another, and this is a true story. Remember I told you how my brain started all this my freshman year in my computer class. Well, also my freshman year, in chemistry class, my professor stated this. And it's funny because it didn't ring a bell in my head till whatever, a decade later when I started learning about all this. But it was a big deal because I remember the professor who was this old dude. He was just so boring. This is like one of the few times he got really excited. He was like trying to be dynamic, And this is what he said. He was talking about entropy. And he said, in order to mathematically model the movement of all the air molecules in the room. So let's pause. There's air in this room, right? Air's molecules, oxygen and nitrogen. It's dispersed. It's being blowed. Okay, there's a flow to it. But and the Boltzmann's statistical formula can model that. And that's what we use in the computer to model where the air is, assuming the fan's not on or whatever.
Yeah.
But in that model, you also have to take into consideration that what if all the air molecules, for whatever reason, decide to bunch up in the corners of the room? They all just move to the corners. And we all suffocate and die because we have no oxygen. Now, the strange thing about this is they had been trying to mathematically model this for a while, and it would never work because they came up with mathematical models for all the things that were plausible. Think about all the stuff that can happen with air in the room, just without the fans being on. And think about a supercomputer, right? Doing trillions of calculations. They did mathematics like that.
Yeah.
The problem was when they applied it to situations in the real world, it didn't work. But when they applied it, this new Boltzmann's equation, it all started to work. But Boltzmann's equation also considered the impossible. Like atoms moving to the corners, everyone's suffocating, what's going on? So what am I saying? In order for entropy to work, it needs to take into account the impossible. So let's translate that to Christianese. Before you can model what happens to someone when they walk off a boat into a body of water and fall in, mathematically, you have to take into consideration, not only take into consideration, you have to acknowledge the fact that it is perfectly conceivable and mathematically possible that when the person walks onto that water, the water molecules will not be moving very much. They'll stop moving, which means the water will be solid, which means the person will walk on water. In other words, miracles, the things science say, oh, that's not possible. And maybe you get some doctors who are like, okay, miracles are possible, but only because we don't understand the science behind it. Mathematically, the foundation, thermodynamics, miracles are not only possible, but they are required to be possible for the world to exist in the chaotic state we know it to be in. So here you can just imagine, first thing said, Bible, that's not possible. Those are stories. You actually believe in these stories. This needs to be possible for the world to work. And that's why the old school, Planck, we're going to talk about him in a second, he's like, no. Entropy must increase, no matter what. Mathematically, he says, all likelihood it's going to increase. But mathematically, it could not increase. Now, here's where you have the problem with how we've been misinterpreting it as far as the evolutionary side. Mathematically speaking, it is quite possible that suddenly things will order and life can happen. Mathematically, it is possible, So that's where I said you can sort of take it away, even though statistically and in our sense, but without the math, I was going to write the equation, but it's basically he has a constant, another constant, Boltzmann's constant, log. Anyone remember what a logarithm is? Logarithm.
I heard it where I just.
A logarithm is the reverse of the power of something. So 10 cubed is 1,000, right? So the logarithm of 1,000 is 3. You just take the exponent. Whatever. It's important. Logarithms are important because A, we see them all over in nature, and it's usually written log or ln, line. And this is what the key is an equation. Which I'm not sure why I threw that out, but there's a freebie, Again, here's something that physicists saw in the 1900s that scientists today are oblivious to. If you ask any scientist today if miracles are possible, and if acting on the scientific part of their brain, they're going to tell you no, they aren't possible, since all their scientific knowledge, like entropy, like their real-world experience, speaks against it.
Right.
No, it can't happen that all the cancer cells suddenly decided to all die or all start working again, or whatever concoction you want to come up with. Well, the fact of the matter is, mathematically, it is untrue. So, in a way, I mean, this isn't so much of a gotcha, but this is proof of miracles right here, In case people are like, oh, there's no scientific proof of miracles. It's right here.
Yeah.
Say entropy, and they'll probably look at you confused, but just run with it. In 1900, scientists were against the statistical nature of entropy for exactly the opposite reason, because it implied miracles must be possible, which scientists don't like to talk about miracles. Because miracles means
God.
a God or some ethereal force, and that's the whole point of science. We're getting away from all that. Remember what Galileo said? No, prove it. Prove it experimentally.
Yeah.
Well, here it is mathematically. You see, Christians use entropy as a means to handily discredit the theory of evolution and how matter and life became more and more organized out of chaos. Yet we miss the simple fact that it is through this same principle, that being entropy, that we can see how miracles are in fact possible. Now here's the sad thing. Nobody believed him. In 1898, he published his detailed calculations. I mean, he just wrote all the math. And he hoped that this would eventually catch on, but it wasn't. And it was crazy because his colleagues and his German colleagues were all, the Germans were heavily against him. Because he was German. But here's the ironic part. He killed himself. He actually committed suicide. Depressed. Which I know with the whole Robin Williams thing, But what's sad is, literally months after he killed himself, some obscure guy named Albert Einstein ended up proving the validity of atoms and his statistical theory. So he literally missed it. And Albert Einstein was German,
Yeah.
So they all were complete idiots. So not only he got the ha-ha, you guys are idiots, you're so smart, Einstein showed you're wrong. So it's kind of sad, suicide. Yeah. Lord Kelvin.
Oh, yeah.
How many heard of Lord Kelvin? Or you've heard of Kelvin, right? Kelvin, temperature. 1824 to 1907. He was the most prominent mathematical physicist and engineer of his time. Like he was, like every generation has a leader. Like he was the leader. He was the first scientist to be named Lord, like Queen Victoria, because of his work on the transatlantic cable. So he's what allowed New York to telegraph Europe. I mean, that's huge. I mean, for all of history, in order to communicate with somebody, you had to send a letter,
Yeah.
And even in modern times, in America, it took months to send a letter to England. Now it was seconds.
Yeah.
This is a big deal.
You take months to send one across the country, too.
I know. In 1894, he famously remarked, "There is nothing new to be discovered in physics now. All that remains is more and more precise measurement." So in the year 1900, scientists were like, we've arrived. We know everything. All we need to know, maybe we don't know everything to exact details, and the example I give is, as funny as that sounds, he has a point. Remember, Newton's laws by 1900 were what, 300 plus years old? They had matrices. They had already worked out electricity and magnetism, which we skipped over. I didn't want to, but maybe we'll come back to stuff in that. But I wanted to try to get on track here, So let's take the measurement of the speed of light. In 1728, they did experiments on the speed of light because they got it to 301 kilometers per second. By 1849, Louis Fizeau got it down to 313,300 kilometers per second. By 1862, Leon Foucault, which his name may sound familiar because the Foucault pendulum, that's what he used, and this is more in Lord Kelvin's time, worked it down to 299,796 kilometers per second. And then in 1879, Michelson took it even closer, 299,790. Oh, you know what? I screwed up. This is the same dang number. One of those numbers, it's just a little bit different. It's more precise. Then, of course, the modern measurement is 299,792.458 kilometers per second, or 186,282 miles per second, which is what we usually use, miles per second. We don't do kilometers. Kilometers are for Europeans. Yeah. But the whole point is that they knew about all these things, and he's just like, look, it's all about, we're just going to get more and more precise detail. You know, we understand electricity, we understand magnetism, we understand forces, we understand, we've arrived. Michael Faraday and James Maxwell. How many of you heard of Michael Faraday or James Maxwell? Which one? Both? Both. Okay. Okay. Michael Faraday and James Maxwell. Without Michael Faraday, there'd be no electricity. Let's put it that way. We wouldn't know how to generate electricity. We wouldn't know how to anything, And Faraday and Maxwell were like the two-part genius. Both of these guys actually. Faraday famously had a portrait of Newton in his office wall because Newton was the man. Ironically, guess who Einstein had on his wall? Faraday and Maxwell. So these were his idols. Like, dude, these are the guys, even though nobody knows who they are. Faraday was the creative genius. Like, he literally had probably the same mathematical skills as most of us in this room. Like, basic algebra. But he could conceptualize and visualize and come up with, he just thought outside the, lines of force. You know how a magnetic field, if you ever do the magnetic filings and those force lines, he formulated a whole working theory using lines of force. Now everyone laughed at him because they're like, okay, that's nice, but, back that thing up, or give me some math, He couldn't do the math, Or he actually did the first work in, what's it called? Electricity and magnetism. How many heard of magnetic induction? Yes, magnetic induction is how we get all our electricity. In case you're wondering where the electricity comes from, One of the first things he realized, here, I'm going to give you electricity in a nutshell. Okay, in 5 minutes, I'm going to do what I did actually 100 slides ago. All right. So they finally figure out electricity. All right, shock, static electricity. Yeah. Then they worked out, finally, Alessandro Volta, you get the volt, he created the battery, voltaic pile. And a battery, just so you know, it's just a chemical reaction. It's a chemical reaction, and we get the electrons in this reaction to run through a wire, and that's how we get our electricity. Right. So he finally works out batteries. And batteries are the way we formulate electricity, and they do all this crazy stuff. The first thing, okay, so you have electricity. The other crazy force we talked about is magnetism. Magnetite or lodgestone, they've known about for forever, all the way back in ancient Egypt. They didn't know what it was. They just know here's a rock, and stuff sticks to it. Like, it's attracted. Like, magnets are pretty crazy when you think about them. Now, we think we know about them, positive, negative, but how can a piece of metal, exude a force that's invisible and push something away? Yeah. Or then you flip it around and it pulls. I mean, it's all very fantastical. And after Newton broke down what forces were, scientists were like, okay, well, what about these other forces? We got to investigate electricity, we got to investigate magnetism. And they did. And one of the first things they discovered is once they got electricity running through a wire, one day, it happened by accident, is he turned on the battery, right? Got a current through it, and he happened to have a compass on the desk. And as soon as the electricity ran through the wire, the compass deflected. And then it came back. This was the first time they saw a link between electricity and magnetism. They were two separate things, Later, what's his name? God, he has a famous name. Because, every unit of measure, Kelvin, Celsius, they're all named after scientists. He realized that if you take two wires with currents going opposite directions, so one current's going this way, while the current's going that way, they're actually attracted to each other magnetically.
Yeah.
And then if you take them and make the currents go the same direction, they're repelled. So we're like, okay. So now they're like, okay, what is this linkage, you know? So Maxwell was a mathematician, super mathematician. He was like the genius of all geniuses. He took all Faraday's work. Now you can't say he took his work, but he made a mathematical description for everything that Michael Faraday had described.
Right.
So Faraday had mathematically shown and all that math, induction and all this stuff. He did lines of force. But Maxwell wrote out mathematically what it all meant. And they're famously called Maxwell's equations. They're a set of 4 partial differential equations. And this ain't no joke. Like, this is like the hardest of the hard math. Like, really difficult. Like, I remember both my physics professors saying, like, you don't want to mess with this, you know, like, it's like graduate level, you know, when you really start working with these equations. It's very, very difficult, the hard, very, very hard calculus. So what's my point? Is that when he finally merged them, that's where we get this notion of the electromagnetic wave, which most of us have heard that, maybe don't know what it means. But that's why all our wires have this shielding, you know, because they have to shield from magnetic force, you know. And so, and just to go, electricity. So electrons running through a wire produce a magnetic field, right? Faraday worked out that the opposite is true. So if you take a magnet, right, and you take a coil of wire, and you move the magnet between the coil of wire, if you have what's called a galvanometer, which measures current,
Yeah.
as soon as you move the magnet through the wire, you'll measure a current.
Yeah.
As soon as you stop, no current. The magnet has to be moving. If you move the magnet up out of the wire, the current shoots the other direction. Move it up, down, up, down. I don't know if you've ever seen those flashlights that charge themselves and you shake them like the hand crank. That is what it's doing, magnetic induction. So if you move a magnet throughout a coiled loop of wire, it doesn't even have to have a current, you will produce a current. Now the classic thing is the whole hand crank. You know, you have a crank, yeah?
That's what I'm going to ask you is that what for the people who are what do you call them? The preparers, like, you know, if something
Yeah, preparers.
is coming, but
Mhm.
people who are prepared, you know, for, you know.
Or they have a bike that produces electricity. That's all they're doing. So what they're doing is they're cranking, they're moving, think of a square-shaped piece of metal, right?
Yeah.
Oh, shoot. I need to make sure I turn my phone off because if it rings, it's going to mess up my recording. Okay. Imagine a ring, right? And in that ring, you wrap a fine coil of wire all along it. And that's attached to the crank. I wish I had my pictures. And outside of it are 2 big magnets. One is positive, one's negative. So one attracts you, it's in the middle. As soon as you crank that and turn it, that produces, and the equations are actually really simple. They have to do with how fast you turn it. That produces a current.
Yeah.
So whether you have a hand crank radio, now what the radio of those hand crank does is that current is then stored inside a battery.
Right.
You know. But even if you didn't have that, a generator, that's how all our power is produced. So think about hydroelectric power, right?
Yeah.
The water, these are big, giant magnets. I mean, magnets the size of this room, right? And really big, heavy crank. No human could turn this crank. But the power of the river does what? It turns it.
Yeah.
So turning that coil of wire inside a magnetic field produces current, and that's how we get power. And that's actually what all of it is. People think that they're different. Like coal, they just burn coal
Yeah.
to produce steam to turn a turbine.
Yeah.
Nuclear power, same thing. They use nuclear rods that, because of nuclear reactions, get really hot. Put them in water, steam. No matter what you do, you're just turning something.
What about solar? Explain.
Oh, solar's different.
Yeah.
Solar's different. Yeah, that's a whole, but still same principles. You know, you're still taking, because what is the sunlight? Electromagnetic waves, electromagnetic radiation.
Yeah.
So they have to take that and convert it a different way. But it's not mechanical in that sense.
Yeah.
The second great unification. Remember how I mentioned how Newton ushered in the first unification, right? He said, on earth as it is in the heavens, right? So he not only broke the barrier, like, hey, everything in heaven works exactly how it does here. Like, they are one and the same. That is a unification, because scientists have always said heavens have these rules, earth has these rules. They've been unified into one. Now that they got going, remember, now the two main forces besides the one Newton described were electricity and magnetism. Maxwell merged them into one. Electricity and magnetism are the same force, the same side of a coin,
Yeah.
which most people don't even realize. They think a magnet's a magnet, electricity is electricity.
Yep.
They're tied together. So this was considered the second great unification in physics. So now you unify the force. And the reason why this is important is because you understand where we're going in science. They're always trying to unify.
Yeah.
Unify. Electricity, magnetism, light. Light.
Yeah.
Besides electricity and magnetism, now we're just like light. Light is light, right? No, light was a huge question mark. What the heck is light?
Yeah.
I mean, I don't know about you, but I never thought about it. It's like it's just light. I mean, I don't know what light is. But this was a big deal. Now, this, of course, this unification brought light under it. But we actually have to go in here, because this is important for later, is what is light? All the early scientists, again, were men of faith. And light, I don't know if you read your Bible, has very powerful biblical significance. You know, let there be light. And there's light, and God is light. The Shekinah glory, light. And there's just light. You know, light. Light is good. And Jesus shines so brightly. In Revelation, there's just light. You know, so what is this light? We know intuitively, we think we know intuitively what it is, but what is it scientifically? Again, you go back to Newton. You know, Newton's theories. Newton, remember, he was dealing with stuff hitting each other, right? Particles, little pieces of matter. So it's no surprise that he thought of light as little pieces of matter, little bits of light, just like, you know, cheese, little bits of cheese, you know. The light has atoms, you know. Light is observed to travel in straight lines, the way light bounces off of mirrors, much like a ball bouncing off a wall. Newton's light theory rested on light consisting of a stream of tiny particles called corpuscles. We call it Newton's corpuscular theory of light. Now today, what do we call these? Little particles of light.
Electrons.
Nope.
Right?
Huh?
Right?
Photons.
Oh, yeah.
That's what a photon is. A photon is a little particle of light. His cutting edge works on optics. And again, he did crazy stuff in optics. All the stuff with your lenses and all that, that was, again, hundreds and hundreds of years old. But he used, everything rested on light being a little stream of little particles reacting like you would lines. And here I threw in here's the cover of his book. Thought it was pretty cool. But here's some modern. This is stuff you do in physics class. And this stuff is just nasty. But, you know, concave, convex lenses, how light refracts. But notice it's straight lines, you know, because that's how Newton worked out. There's a stream of tiny particles, and of course you take them and you bend them, and and focal points, and yes.
I got to throw in some Bible.
Oh, yes.
John 8:12, and Jesus spoke to them again, saying, I am the light of the world. He who follows me shall not walk in darkness, but have the light of life. And he said, narrow is the way to the kingdom, you know, so, and it's straight and narrow, so light. So to me, it's like, anyway, that's fine. I'm just looking at
That's
straight.
good. No, that's anytime you have revelation, more than welcome to interrupt, you know.
He
It's
said
not
light
interrupted.
is always straight, and so he's a light, and so, you know, narrow is the way. So anyway, that's what I saw.
But Newton's ideas weren't the only ideas. There was another guy, his contemporary. He was a Frenchman. Nobody in Britain liked French people, you know. His name is Christian Huygens. He was a prominent Dutch mathematician and scientist, but he was Dutch, but he did everything in France and Paris, whatever. He didn't think light was made up of a hail of tiny particles, as Newton did. He just wasn't convinced. He's like, no, I think you got it wrong. In 1690, he published his treatise on light in Paris. And there's the cover. He described light as a wave. He's like, no, light is not little pieces of matter. Light is just like in a pond, you know? You drop a rock in a pond, and what do you get? It's a ripple. Those are waves. He said that is what light is. And he was able to show all the things Newton did, but using waves. So you could work it out either or, you know? Now, of course, each theory had its pluses and minuses. Quite simply, he explained optics, refraction, and color by representing light as a wave. Now, Newton, of course, had considered light as a wave, but he ended up dismissing it for a lot of reasons. And here was his main reason. Oh, here's a little animation. Again, this was huge too because white light was considered the pure light, like it was the light of God. It was pure. And colored light was tainted. And Newton showed actually white light is the culmination of everything. So all those tainted lesser things, you don't get white, so they're all combined together. Little side note. So a wave, much like a wave in a pond, needs a medium in which to propagate through. So this was a big thing because when you drop a rock, the waves propagate what? Through the water.
Yeah.
Now we talk, sound waves. You all heard of sound waves, right?
Yeah.
They propagate through the air. They're micro bursts and they do change in pressure, but they're waves.
Yeah.
The whole alien in space, no one can hear you scream. Like, no, really.
Yeah.
No one can hear you scream. In a vacuum, there's no sound. So no one can hear you scream because you can't make any noise. So, if light was a wave, according to Newton, then there had to be something for it to go through.
Yeah.
Like, I don't
Yeah,
know.
that's fair.
They called it the ether. How many have heard of the ether? I mean, usually, ever since I started putting this class about 6 months ago, I swear it's like the slug bug effect, like everywhere. I hear people praying, they're talking about in the ether, You hear it, usually you hear any movies about the 1800s, and usually they talked about it a lot, the ether. It's in the ether. And, of course, New Age people like ether and whatever. But even a lot of Christians I've heard, they're not using it. It's in the side of their brain. I don't blame them. I'm not going to name them, But there's some prominent figures at the church, But just kind of like, they're just making a statement, It's like, oh, it's in the ether, Well, that's what the ether is. The ether, in order for light to move as a wave, there's a substance everywhere. You can't see it. It's like air, but it's not air. And it's called the ether. All right? All empty space around us is not really empty, but it's an invisible substance called the ether, the luminiferous ether. Now, Newton had issues with this because he formulated all his equations by what? We went over that in detail.
Right.
In space, vacuum. So if the heavens were filled with this ether, then the planet's motions would be impeded by this ether. Now, of course, it's very subtle, but essentially all his equations would be off. They would all fail. Like, everything, Newton's gravitational and everything that they saw in the heavens worked because the planets were moving in a vacuum, no other force except for the force of gravity.
Right.
Now you're saying there's this ether that's like syrup. Think of it as syrup, and you got to sludge through it. Obviously, it's not as thick as syrup. But Newton was like, no, this ether is nonsense. So now you had two theories, which for all practical purposes were equal in their strengths and weaknesses. However, obviously the cards are stacked in Newton's favor. Newton was the man. And being the genius that he was, why not go with his theory? I mean, to be honest, here's this dude who's genius, but he's just your normal scientist who has one great idea. Then there's Newton who, gave birth to science and he is you can't underestimate the level of genius awesomeness that Newton was, And so, if Newton says one thing and some other dude says another thing, you're going to go with Newton. Case in point. To make matters worse for Huygens was that the theory could not account for Newton's reconstituting colored light back into white light.
Right.
So Newton did a simple experiment that he couldn't explain using his theory. Is that obviously you take a prism, right?
Yeah.
You shine through it, it goes out the rainbow colors, right? Newton, his thing had it not as waves, but as, corpuscles. He's like, no, they're waves. So Newton then took those and did another prism and refocused them back into white light. Mathematically, he couldn't work it out. So Newton, on top of the fact that he was Newton, it died. So for the next century, for 100 years, this was de facto. Newton's corpuscular theory of light would remain for the most part unchallenged. I say the most part is because it stayed alive in France. The French people were always like, je sais quoi, les poissons, les poissons. They're like, we know better than the stupid British. Now we come to Thomas Young. Thomas Young was a brilliant physicist, musician, doctor. He actually worked out astigmatism, the shape of the eye. He actually formulated the first contact lens. By the age of 12, he spoke 12 languages. And he was instrumental in work on the Rosetta Stone. How many have heard of Rosetta Stone? What is Rosetta Stone? True, yes. Anyone know another Rosetta Stone.
Yeah, it was a Babylonian stela or something like that. It was a stela.
Yes, it actually was a historical artifact that it was based off of. And here it is. It's a large granite stone inscribed with the decree issued at Memphis in 196 BC on behalf of King Ptolemy V. Now, what it says is inconsequential. It's just sort of lame. Who cares? But the thing about it is the same message was written 3 times in 3 different languages. The top one was ancient Egyptian. The middle one was Demotic script, which is the current language that they speak in Egypt, that they did even 2,000 years ago. And the bottom part is ancient Greek. So this was a big deal because people forget hieroglyphic language was lost for over 1,000 years. Nobody, like even ancient Greece, they didn't know what it said, even though they could have figured it out. They found the right people, obviously, But it's like it was lost. And so this was huge. And this is how we got to decode the hieroglyphics. And it was very difficult. And Thomas Young actually did most of the work, but he didn't get any credit because he was under the other dude. I forgot his name. Who cares? But I actually got to see this. That's why I put this in here. I thought it was cool. When I was in London at the museum, it's 44 inches high, 29.8 inches wide, 11 inches thick, weighs 1,680 pounds. Here's a close-up. Pretty cool.
Wow. So, Valentino, are you saying that they found that in, you said, what was it, 180?
198 BC.
180 BC, so okay, before our Lord came.
Before the Lord came, as one of the last of the pharaohs, the last of the pharaohs.
And they found that where in Memphis, which is...
Memphis. It was buried in the sand. They just found it. And again, all it says is like, I killed this many people, and the Egyptians, whatever, just bragging.
Yeah.
But at that time, he did it in the 3 main languages of the kingdom. And obviously Greek was alive,
So he did it in 3 different languages, which were the same, it was the same, but all the different languages
Yes.
that way they knew, and then that's how they were...
Yes. So like in Rome ruled over like 20 different languages. Now they all spoke, what do they all speak? Aramaic or Greek? Yeah. Whatever. They all spoke Roman.
I think it was Greek and Latin.
Yeah, Greek and Latin, yeah. But he was like, look, here it is for everybody. The common tongue was the middle one, the Demotic. That was the common tongue. But also Egypt spread up north into Greece, Remember Ptolemy was a Greek Egyptian? Greek Egyptian. So they had to do Greek. But somebody at this time still knew the hieroglyphics, So that's how they decoded it. So he doubted Newton's theory of light, and instead he saw Hutchins' theory as the supreme one. He had his own reasons, But being the genius that he was, he actually provided an extremely simple experiment to prove once and for all that light is in fact a wave. Now remember, it's been 100 years, it's been a century that light is a corpuscle or photon, whatever you want to call it. So here's the experiment. The double slit experiment. How many heard of this? Basically it says this. If you take a slit, there's 2 slits, take one slit, right? Newton said light is the little tiny particles. So if you shine light through that one slit and you have something on the wall, what will you get? You'll get one beam of light, right? Now if you have a wave and you work out the mathematics, it does the same thing. The wave goes through and it does one beam of light. But the beam of light kind of, falls off, whatever, So you work out next. But now what if you had 2 slits? If you had 2 slits, if Newton was right, you'd have 2 beams of light.
Right.
But if light was a wave, like Hutchins had been saying for a century, you would have what's called interference patterns. So just like you drop 2 rocks, and you know how the waves, and they hit each other, they do that thing. You know what it is in your head instinctively. It's called interference, where the top of one wave meets the bottom of another wave, they sort of cancel each other out. And if they hit each other, then they'll amplify each other. When you do that, you'll see you get 1, 2, in this example, you get 5 bars of light. And they don't even line up. See, they don't even line up. Actually, the main bar is in the middle, where there's no light, And then the middle bar is thickest, and they get thinner and thinner. Here's a little, that's kind of mathematical, but let me show you a little video I found on YouTube that explains it.
The infamous double slit experiment.
It's easier to see.
To understand this experiment, we first need to see how particles, or little balls of matter, act.
So this is
If we
Newton.
randomly
Newton said
shoot
light
a
does
small
this.
object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit.
So this is what
Now,
light does, right?
If we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity.
So there's a fall off, but you
This
can
is
explain
similar
that
to the
using
line
little
the marbles
pieces,
make.
you know.
But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out.
Yeah.
So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So,
So does that make more sense than my little two-dimensional picture, you know? Another way to look at it is if you look at it two-dimensionally, you know, a wave goes like this, right?
Yeah.
If the top, the crest, lines up with the trough, they cancel each other out. They're opposite.
Yeah.
Where if the top of one meets the top of another one, then it's amplified. You know? So you can look at it two-dimensionally that way. So that is how he did it. So very simple, and you can do this actually at home. You can use it using a laser, and you get two pieces of pencil lead. You put them together, or three pieces of pencil lead, and of course they're little tiny slits. And if you shine the laser through, you'll see it make the little spread out little dots. Here it is again. All right, so now light was a wave. The ether was back. So for 100 years, the ether was gone, but now light's a wave. So now scientists had to deal with the ether. What is the ether? Oh, and here is, no, hold on, I should have done that. So let me go forwards first. So again, Maxwell, in his merging of that, he now explained light. This other crazy thing is light was now an electromagnetic wave. Light is part of electricity and part of magnetism. It's an electromagnetic wave. And that just tripped everybody out. You know, and here is the electromagnetic spectrum. I wish I had blown this up. But basically, if you go to increasing wavelength, so let's look at FM radio, right? A wavelength is this. And it goes up, down, and back.
Yeah.
So that's one wavelength. Everyone on board? So for a radio wave, that wavelength is 10 meters long.
Yeah.
So 33 feet. So what, this whole room. So one wave is as long as this whole room. Like, I'm talking about in the real world. That's how big it is, you know? You go to AM, it's 10 to the 2. It's 100 meters long. So it's a football field. One wave. And then when you go to long radio waves, and you heard of shortwave radio?
Yeah.
That's what you get in disaster, emergency preparation, whatever. The shortwave radios go up to 10 to the 8. So thousands of miles long. And shortwave radios are crazy because when the world ends, or whatever, you know, and all is lost, a shortwave radio is how to go. Because a shortwave radio, you don't need a big powerful antenna or whatever. Like a simple scientist could produce a little thing to send out a shortwave and it will go everywhere, you know. And, you know, if you're worried about media bias, you know, like the media, the lamestream media is tricking you, you get a shortwave radio. Because a shortwave radio, you can pick up on radio stations in India, in China, in Israel. Because on shortwave, they go literally up into what's called the ionosphere.
Yeah.
And they literally bounce around the entire globe. They do this for days. So you can listen to transmissions from 3 days ago from a little town in India on shortwave radio. Pretty cool. Now, if you go the other direction, as the waves get smaller, you go to microwaves.
Yeah.
Microwaves are 10 to the minus 2. So 10 to the minus 2 meter. Okay, microwaves are whatever, this long. All right. Now, microwaves, we all know microwaves because that's how we cook our food, you know. And in case you're wondering how microwaves work, it's because that wave of energy excites the molecules in your food. That's why, like, if you put a napkin in the microwave, it doesn't burst into flames, you know. Well, how come? Aren't you heating it up? Like, no, you're exciting them, but when you excite napkin molecules, not much happens. You know? As it gets smaller and smaller, 10 to the negative 6, so now we're really tiny, like nanometers. This little band here, oh, hold on, let's go. Right before, after microwave, when you get smaller, is infrared. Now, we all have heard of infrared light, right? Infrared light is what the biggest use is your remote control, your clicker. That actually shoots light. You can't see it, Or night vision, infrared. This little slit here, if we blow it up and expand it out, this is 700 nanometers. So we're talking like, most of y'all remember, nano is a billionth of a meter, very small. This band from here to here is what we see visually. So that's all light is. Now, if it gets a little bit smaller, then it goes to ultraviolet. Most of you heard ultraviolet. Biggest thing there is the sun. That's how you get a tan or sunburn for some of you. Or with your money, the UV, the black light, that's ultraviolet. Once you get even smaller, you do X-rays. That's why these things are so useful, because they're so small, they can go right through your flesh, but they don't go through your bones, so that's how you get a picture of your bones. And if you get even smaller, that's when you go to the Hulk. Gamma rays. That's how the Hulk was made, and that's where Marvel comes from. And these are ridiculously small, like 10 to the negative 16. That's like a trillionth of a trillion.
That's like
A trillionth of a billionth. It's very small. Now, in the other direction here is frequency. The frequency is how many of these per second. That's what a hertz is.
yeah.
So for AM, we'll go to long radio waves, right? So they're like 1,000 miles long, but every second just one of them goes by. Then by the time they get to AM, it's 10 to the 6. So 6 zeros is a million. So with an AM radio wave, if you were to see it, 1 million of them, of these waves, would go by you in a second. So very, very fast. Can't see that. Radio waves is 10 to the 8th. So it's 100 million, Microwave is 10 to the 10th, now you're like a billion. Infrared, 10 to the 12th, 10 to the 14th. By the time we get into visible light, it's 10 to the 7th, so trillion. And then ultraviolet, by the time you get to gamma rays, it's quadrillion, 10 to the 24th. So a trillion is 4. So a trillion go by a second. That's the intensity. That's like how, remember, the light, if you think of it as energy, the faster they're going and the closer they are, the more energetic they are. That's why radiation,
Yeah.
all the radiation you don't want to get from nuclear bombs, this is all gamma rays, Even X-rays. X-ray technicians, they got to wear like a vest, because they're still, even if you're not in the gamma rays, the X-rays are radioactive. They're going to cause issues, And then you have ultraviolet, blah, blah, blah. So there's your quick cap. Oh, I actually included a little video.
Electromagnetic
From
radiation
YouTube.
travels in waves. Frequency describes how many waves per second a wavelength produces. Wavelength measures the length of an individual wave in meters. Scientists describe the electromagnetic spectrum as a long line. At one end lie radio waves, with the longest wavelengths and lowest frequencies in the spectrum. A single radio wave has the length of a football field. After radio waves come microwaves, which produce more energy due to shorter wavelengths and higher frequencies. Cell phones, radar, and microwave ovens use microwaves. Next comes infrared light. The sun, fire, living creatures, and other heat sources all produce infrared light. While we cannot see infrared light, we feel it as heat. Visible light occupies a narrow slice of the electromagnetic spectrum, nestled between infrared and ultraviolet light. Red wavelengths have the lowest frequencies and longest wavelengths of visible light. As you move from red through orange, yellow, green, blue, and finally violet, wavelengths shorten and frequencies increase. From visible violet light, we move into ultraviolet frequencies. Human skin produces vitamin D when exposed to ultraviolet light, but excessive ultraviolet light causes sunburns. Next, X-rays, which pass through soft tissue but not denser materials such as bone, making them valuable for medical tests. X-rays also have security applications such as airport baggage checks. Gamma rays produce even shorter wavelengths, higher frequencies, and more energy. In comparison to the football field-sized wavelengths of radio waves, gamma ray wavelengths are as small as atom nuclei.
There you go.
And
There's the YouTube weird little nerdy chick version. Now this, I'm just going to add in since I'm a tech geek and I just can't help myself. CDs. Yeah, everyone knows what CDs, DVDs, right? Whether you know this or not, a CD is digital, right? Everyone knows they're digital?
Yep.
And you know what that means. And now I already explained to you, digital means ones and zeros.
Yep.
So if you look under a microscope on a CD, you'll see little pits. So a 0 is like a little circle, right? And a 1 is like an oval, and they're just in a row. So what the CD does is it takes this red light, right? And if it's a 0, it reflects up at a certain angle.
Right.
And the little reader reads a 0. And of course, if it is in a long pit, the deflection angle is different. It reads a 1. And the CD spins at 5,200 RPMs really fast. That's how the CD works. Now, also, if you remember, a CD is 740 megabytes, whatever. All right, it's not a lot of data in today's standards. Then a DVD came out, remember? So now they want to fit movies. But movies are like 4.7 gigabytes. And actually, the ones Hollywood uses are 8 gigabytes.
Yeah.
So instead of 700 megabytes on a CD, you have 8,000 megabytes on a DVD. Well, how did they do this? They needed to make all those little those pits smaller. Well, if you made them smaller, you needed a smaller frequency of light. So then they moved up to, because in CD players, if you can look now, you can actually see the red laser.
Yeah.
On DVD, you don't see it anymore. It's actually, it's green. Well, it's green. We're not to Blu-ray yet. We're green. And that's the whole point where I'm getting at. And then, of course, after DVDs, the Blu-ray came out, and everyone stopped caring.
So is that why it's?
That's why it's called Blu-ray.
Yeah, it needs to be ultra ray.
Yeah. And they were working on Ultra Ray, but, the time has passed. People aren't really buying this, And actually,
Going on the internet.
they now surpassed this because they have a holographic
Yeah.
digital storage, which holds vastly more. Yeah.
I know you've heard of this. What's up? You just triggered my mind of the holographic. Isn't there something with video games that they're coming out with? It's almost like the idea of Wii and what's the? I know you guys know PlayStation. Is it 4 that has something similar to the Wii or somewhere to connect with it? Anyway, something about I was in Xbox One or something. Eventually, their goal is to have like hologram video games where you're literally it feels like you're in the game. It's crazy.
Oh, yeah, Oculus Rift.
Yeah.
What is it?
Oculus Rift?
Okay, yeah, something crazy. It's
Yeah.
really,
Little element that you put
yeah,
on
it
it.
seems to me pretty it could get demonic going too far for me. It's like, whoa, that's a little.
Well, remember, the ultimate goal is Star Trek. That's what I always do, the holodeck. This could all be a hologram, It's like we all know what light is, and now that the science gets advanced enough where they can control it, manipulate it, and even give it substance, and it's pretty trippy.
Yeah, it sounds like Revelation 13.
But now you guys understand light, all right? So again, this was a huge merging, all these ideas merging together. So you can understand why scientists, or Lord Kelvin was pretty cocky. He was like, look, we got this figured out. But despite all this, he had also great foresight.
Yeah.
In 1900, towards the very end, when he's old, he gave a series of lectures called 19th Century Clouds over the dynamical theory of heat and light.
Yeah.
And basically, he foresaw 2 dark clouds on the horizon. So he was like, look, we know everything, but there's 2 areas in particular that we can't explain, and it causes problems. What were those 2 areas? The 2 dark clouds alluded to are a phenomenon that science at the time could at best give unsatisfactory explanations for. The Michelson-Morley experiment and black body radiation. Now, we'll go over these in details later, but basically, the Michelson-Morley experiment proved once and for all that there was no ether.
Yeah.
Now, this was a big deal because they're like, light's a wave. Of course, light's also a particle. Life and the dead, but we'll get to that, Light is whatever you want it to be, really, It could be a compact piece of something, or it could be a spread out wavy thing,
Yeah.
But the Michelson-Morley experiment was a huge deal for them because it was advanced enough and everybody was on board with the results. They're like, okay, there is no ether. That's where Einstein and relativity kind of stepped in,
Yeah.
The other one was black body radiation. Basically, a hot poker. You put a poker in a fire and it gets hot. Well, why is that a big deal? Remember, scientists, especially after merging all this, after everything's being merged, what are you left with, right? You're left with matter, little pieces of something, and you're left with electromagnetic waves. Well, what's the common denominator? Like, you can't, I'm perfectly okay with one thing and another thing, but they're like, no, what is the common denominator? So if you think of a hot poker, here's matter. It's moving around, vibrating. It's light, but what is it doing? It's emitting light.
Yeah.
It's emitting heat. So if they can figure out how matter produces waves, that can help them find out what's the common core. Does that make sense?
Yeah.
So the 20th century would produce two theories that would address each of these concerns. So blackbody radiation would be addressed and answered by quantum theory. So, what's my next slide?
Cool.
Oh, these two theories would form the foundation of our current understanding in science. Theory of relativity and quantum theory. So just to be clear, as of 2014, August, 15th, as of right now in science, they pretty much can explain everything. Now, even the things they can't explain, like all the stuff about black holes and dark matter, they only know because of the theory. So it's like, they wouldn't even know about that stuff if it wasn't for this. But everything can be explained with one or the other. The funny thing is like the small stuff, quantum mechanics, right? The atomic, which we're breaking down. As things get bigger, you can still do atomic theory, but it's easier just to use Newton, classical, whatever. Newton's theories work fine. You know, it turns out Newton's laws were wrong. You know, Newton was off by a billionth of a trillionth of a meter. So it works with billiard balls, it works with really small balls, but when they get small enough, they stop working. So again, quantum theory. Then when you get into space, you reach this invisible like wall, where once things start going really fast, like towards the speed of light, and once things get really big, like planets, quantum theory just disintegrates. But scientists switch over to relativity. So again, scientists are happy because between the two theories, they can sort of explain everything, but obviously you're missing something. Because these two theories are not compatible at all. So that's the whole goal of the Large Hadron Collider. That's the goal of all of this is like, look, actually everything they're doing in particle physics, all it is proving quantum theory. Relativity, basically gravity. They cannot for the life of themselves explain gravity in the terms of quantum theory. They're two just opposing things. My point is that's where we're pushed right now. To this day, we're still trying to merge, still trying to simplify. Because the one thing science has shown us, and Einstein will show us next when he rewrites the world, is he writes these beautiful, simple equations, you know, that you can simplify, make things simpler. So dual philosophies. This is everything I just said. Yes, okay. So, anytime they try to explain how electromagnetic radiation dealt with matter, their stuff just fell apart. And if they tried to explain light without an ether, they were lost, even though the experiment said there is no ether. There's no magical mist that light propagates through. I didn't realize what time it was. Dang it. Oh, well, it's good. Okay. So black body radiation. Hot poker. Everyone loves hot poker. That didn't make much sense, but... So a hot object radiates electromagnetic energy in the form of heat and light, right? The hotter it is, the more energy it radiates. So a red hot poker is cooler than a white hot poker. Imagine if you got a poker blue, it's really hot. But here's the funny thing. Even if the poker's not hot, it's still radiating energy.
Yeah.
But it's at a lower frequency.
Yeah.
So I just have to. Here's your revelation right here. I'll use this one. Okay. What does the Bible say, TJ, about light? Remember, at one time we emitted light, right? The Shekinah glory. Adam and Eve were bathed in light. And as our sin, as we fell, we lost that glory. We no longer glow, right?
Yeah, because Moses did when he came down from
Exactly. Exactly. But that's actually wrong. Look, infrared. What's another name for infrared rays? What about infrared vision?
Yeah.
Predator,
Yeah.
heat vision.
Yeah.
So the predator sees infrared light. He sees it just a little bit less intense. So your heat, that's actually light.
Yeah.
So we are radiating light. But unlike Moses, who's radiating in the visible spectrum, our light is weakened. Weakened how? Our waves are longer and they're not as fast. So the intensity, basically we're dimmed. Moses, not dimmed. Jesus, really not dimmed. But it's interesting to point out that we are emitting light. Now, infrared light, now you can argue about it. That's what people, it's not really light. X-rays aren't light, but whatever. I mean, visible light is this one shred. But technically speaking, scientifically speaking, we are emitting electromagnetic rays. They're just not powerful enough to be like they were for Moses and Adam and Eve. But it's kind of cool scientific fact.
Is that kind of what happened when they saw, when Peter and John, and who was the other gentleman with him, when Jesus was on the Mount of Transfiguration? Kind of like, is that same situation kind of similar? Moses and Jesus, of course, and now Jesus up in the Mount of Transfiguration. Now you're saying that he was basically radiating light, and he, I guess, was it met with Moses and Elijah? Yeah. So do you think is that a similar situation?
Well, yeah, that's just the point is remember, you always have to. Sometimes I don't make the connections as clear. Remember, the whole purpose of all this I'm teaching you is to make things that were biblical heebie-jeebie into reality. So my hope is before this class, someone to be like, really, like Moses glowed, like not a J-Lo glow, like he really glowed. That's not scientific. That's folklore. No, I'm telling you, it is scientific. We are radiating electromagnetic energy. Now it's not light because it's weaker, but you could conceivably say what could give them a little boost. Like their electromagnetic radiation is a little bit more intense. I'm giving you a scientific reasoning how Jesus' eyes really could scientifically glow like fire. His hair, his clothes just aren't so clean they reflect light well. Like he really is glowing white light, and he has really clean wool clothes. So the hotter it is, the more energy. Red hot poker, I already said that. Okay. So it's fairly obvious at the end of the 20th century that this electromagnetic radiation must be associated with the movement of tiny electrical charges. So the electron had only just been discovered, and I skipped over that, but they started to realize the atom's not the smallest part, and they actually did it using the cathode ray tube and the precursor to the television, But they found that an atom, if you stripped it down, I don't know if you ever heard of an alpha particle. Like hydrogen is the most basic atom. And if you strip off its electron, you have like a naked atom. It's like an alpha particle. And if you do that, they found out that using magnetic things, you could find that the hydrogen, the protons and neutrons would hit something, but something else would come off. And using magnets, they could see that these things were negatively charged. That's how we get charge. Electrons have a negative charge.
Yeah.
Protons have a positive charge. I'm not sure how I got off on that tangent. Oh, here's the point. So their thinking is this. You heat something, it moves really fast, right? If something's moving really fast, what is it doing? It's waving. So it's moving really fast and it's emitting a wave. Like, how is that happening? How can we work this out? Because that will help us understand that maybe waves aren't really waves at all. Maybe waves are actually just matter. Here's the trouble, was that the combination of the best classical theories, statistical mechanics, and electromagnetism predicted a form of radiation very different from the kind actually observed from hot objects. What does that mean? You take a poker, right? You imagine it gets warm and it glows to red hot. This is the curve. If you were to curve this is at 3,000 Kelvin. So whatever, like 5,000 degrees. If you were to curve that temperature, here's the wavelength. Now this on the right side is infrared, so you can't see it. This little rainbow, I don't know if you can see it, is the realm of the visible spectrum. And then it curves down to nothing. So when it gets hot, we can see that the light is intense, or it falls off, and it gets intense, and then it obviously stops, because you go outside the spectrum. And then, but eventually, even though you can't see the light, it will eventually taper down. Okay? This is what we see. Not a big deal. If you take it at more, and it does with all the frequencies. So the top frequency, take it at 4,000 Kelvin. This is really hot. Same thing. Obviously, something that's really hot, white hot, it's glowing. much brighter. This is brightness here. So it's glowing much brighter. The green goes up, and then you lose it, and it tapers down. Because they found ways to see infrared even back then, and they used filters and all that, you know. What's the point of this? Maxwell, his awesome equations, everything in science, Lord Kelvin, everything they knew, they could work out mathematically. This is exactly what happens. We're cool, we're kosher, you know. We are geniuses, we are men, and we worked out mathematically what we see in the world. Not really. Because what happens if things get a little bit too hot? And that's what it says. So now let's take it the next step. Let's take it 5,000 kelvins. All right? This is what we see happen. Now, this is when stuff glows like stupid blue hot. Like you got to be as hot as the sun to even have this happen. But and it's after it's already melted. It's liquid. But the point being is you see the same trend. Obviously, it's much brighter. This is really bright. You know, there's actually some really cool reactions. I was hoping to do one in class. You could do with a lithium battery, and it's kind of crazy. But you can get this reaction, and the light is like brighter than the sun. Like literally, it's so bright we'd all have to like close your eyes to it. Like you can turn off the lights. It's fantastical, you know. But this is really bright, you know. And then you see it's a fall off. Same type of thing. And you can imagine there's all the lines in between. Here's the problem. The equations did not support this. This is what Maxwell, equations, all of science, everything since Newton said this. It was called the ultraviolet catastrophe. Meaning, at certain temperatures, according to the math, you reach a certain level and literally the metal would burst into radiation, burst into ultraviolet light, you know. Like, it goes way off. So this is a major thing of contention is, what are we missing? Like, what's off? You know? We are men, we know everything, you know, but this is relatively simple. This is heating metal up, you know? Why are we not getting what the math... Remember, this math works everywhere else. All our electronics work off this math, you know? This is solid stuff. It's what's called the ultraviolet catastrophe. Now, all is quite not lost, since classical physics seems to be half right. So on the low-frequency side, the observations agree very well with classical predictions. The puzzle is why the energy of the high oscillations at high frequencies are not only very large, but they actually fall away to zero. So it's not so much that, it's one thing if what we see in nature would sort of look like it, but no, it's like it goes up, but then it goes back down. Like, this is totally different math. Scientists are really smart. They split the issue in half, and they came out with two formulas. You know, two different scientific laws that apply to the low-frequency side and the high-frequency side. The Rayleigh-Jeans law, which is the classical electrodynamic law, is a formula that predicts exactly for the lower frequencies, right? Then this other guy, Wiens, he came out with a math, beautifully worked out, that explained the high-end curve. So now the thing is, okay, you have two different scientific laws. Where's this switch happening? Why is it when you heat up to a certain temperature, suddenly you got to switch to a different equation? Like, what's the common denominator? And that's where we come to Max Planck. Now, sadly, I watched a video that corrected me. It's Max Planck. But we're going to stick with Planck. Yeah. He's German, yeah. So again, this is, even though in the 1900s everybody knew everything, but if you're going to get into something, let's go into one of these areas. So that's where he went, you know. His specialty was in the area of thermodynamics. He hoped to resolve the ultraviolet catastrophe by means of applying thermodynamic rules. He worked extensively on this problem from 1895 to 1900. In 1900, he made a breakthrough. Not through a calm scientific process, but as an act of desperation. A wonderful mix of luck and insight with a fortunate misunderstanding of one of the mathematical tools he was using. So what do I mean? Planck decided to work backwards. So he spent years getting nowhere. He's like, you know what, look, I know the result. So let me just number fudge, and let me find an equation that sort of works. And then we'll figure out how that equation can work later, you know. So he did that. He realized the two incomplete descriptions of black-body spectrum could be combined into one simple mathematical formula that described the shape of the whole curve. Planck's equation agreed beautifully with the observed results. But unlike the two halves for which it was built, it had no physical basis. Remember, he's not going to publish this till he finds some basis. Planck spent the following months immersing himself in the problem of finding a physical basis for his law, trying out different combinations of physical assumptions, but none of them worked. He later remarked that this was the most intensive period of work in his entire life. All his attempts had failed until he was left with only one option, which to him was completely unattractive. What do you think that was?
Ask for help.
Yeah. He had help, actually. There was something there, but he didn't want to touch it. And what was that? He was from the old school. I spelled that right. He was reluctant to accept many current ideas, and especially abhorred the idea of the statistical interpretation of the property known as entropy, an interpretation introduced by Boltzmann into the science of thermodynamics. Planck was one of the Germans that drove him to suicide. Like, dude, you're an idiot. Entropy must increase. I don't care what your equations say. Now, years later, he's like, I should try these equations out. I should try the math out, but I don't want to because they're stupid, you know. For him, entropy must always increase, and probabilities don't enter into it. So it's easy to understand how Planck must have felt near the end of 1900. Having been exhausted of all other ideas, he reluctantly tried to incorporate Boltzmann's statistical version of thermodynamics into his calculations, only to find that they worked. So now he worked it out. It worked. But he's so pissed. It's just, you can't imagine how pissed he is. The irony of the situation, this is what makes it even funnier. Not only did he use something he abhorred, only reason why it worked is because he didn't know what he was doing. Remember, if you don't care about something, you don't take the chance to learn about it and how it works, right? He applied the mathematics incorrectly. Now, so he got the right answer for the wrong reason. Well, what does that mean? Remember, if you look at energy, it's really simple. I don't know if any of you guys know about calculus, right? Calculus is that math that's really hard. A. B, all calculus is if you take a line, take a weird shape, right? And you want to measure its area. Now, a circle, we know a circle, right? It's curved. The way you do that is you have to cut it up into little pieces. And you can measure each piece, right? Because each piece is a rectangle with a curved top. Then you got to cut those up into little pieces. And if you cut a curve into little pieces, you get another rectangle with a little curved top. And you keep cutting it to infinity, which sounds really bizarre. So you cut an infinite amount of slices. That's what calculus is. And then you add them all together. Now this works. It just does. This is the foundation of our buildings. And if this didn't work, then we wouldn't be able to calculate stresses and tensions, and we wouldn't be able to trust going into anything more than 2 stories, you know. But basically what he did was he cut the chunks up, the energy. He cut the chunks up into bits. But he didn't add them back together. A, he didn't know better. But B, even if he knew better, once he cut the bits into chunks, it worked. If you were to add them back together, you got the ultraviolet catastrophe all right back. So he had to stop at cutting things into chunks. The energy divided up into portions before this part of the calculation then had to be added together. This is what I just said. I need to stop talking before my slides. Halfway through this, though, Planck realized he had a mathematical formula he was looking for and skipped the last step of integration. This was a drastic step and completely unjustified within the context of classical physics. Any other physicist would have completed the integration, though it would not have worked, and found that they restored the ultraviolet catastrophe. It was only because Planck knew the answer he was looking for that he was able to stop short of the full, seemingly correct classical solution to the equations. As a result, he was left with pieces of energy that had to be explained. What does this mean? He interpreted this parent division of electromagnetic energy into individual pieces as meaning that the electric oscillators inside of an atom could only emit or absorb energy in lumps of a certain size called quanta. So this is where quantum comes from. Quantum is plural for quantum.
Yeah.
Energy. Now this applies to length as well. So this is a weird concept. Energy is not continuous. All right? So if you have energy, one What's an energy we can all agree on? Volts. You don't even know what volts are. 1 volt, all right? You can have half a volt, right? Millivolt, 1/1,000,000th of a volt. And you assume that you can keep getting smaller and smaller, right? Eventually you reach a limit. There's the smallest piece of energy. And it's called a quanta. A quanta, meaning things are cut up into chunks. Oh, we'll go over the equation in a second. So here's a wave. Think of it like a radio wave. Now, any you guys know about audio? What don't you know about? A computer can't model an audio wave. What it does, if you zoom in enough, remember, computers only know ones and zeros. So what does a computer do? It's like a staircase. It's very rigid. But it's called subsampling. If you sample your little staircase enough times, like 1 billion times within like a centimeter, and you zoom out, it's like a smooth curve. So the real world is the same thing. It's quantized. Now this is where you start getting people saying that the universe is digital, because literally the universe is not 0 and 1. It's 0 and what's this number, which Planck called Planck's constant. It's a very, 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 very small number. Energy is not continuous, but is quantized, meaning it has an absolute lower limit. Think about, ATM. That's what I was getting at. So another way to think about it is think about money. Like we all know about money. And imagine a nickel was the smallest. There's nothing smaller than a nickel. Like, dude, we know there's 5 pennies in a nickel. But no, you cannot split a nickel into 5 pennies. Stranger still, all our money was multiples of 5, right? Because if you can't split a nickel, there is no such thing as a penny. So everything in the world is actually divisible by this little constant, Now the same thing is true with length. Length is quantized. So again, you're thinking, look at a ruler, right? The smallest little dashes are the millimeters, right? You can barely see against them. But there's stuff smaller than that, like a hair, So you can imagine them blowing up the scale and making it smaller, right? And you could blow up the scale some more and make it smaller. Well, eventually, there is a unit. That is the absolute smallest unit. What happens to something smaller than the smallest unit? Like electrons and protons and neutrons. They're smaller than what you can't measure them. This is pretty bizarre, And this is the first clue into the world. And actually, thinking about this, it should start making you question even stuff that you accepted before, like the speed of light. Now, apparently we're okay with the light being the fastest thing ever because it goes so fast. But let's slow it down. Imagine the speed of light was 100 miles per hour. So my little rut putt and his car is designed much better than my rut putt. But it doesn't matter how. You're driving a Ferrari. You cannot go past 100 miles an hour. You know what the speed of light means? That's what it means. There's an absolute speed limit. It doesn't matter how big your engine is. You go 99.999999. You can't even hit the speed of light, actually. So you can get as close as you want to it, 9999999 to a trillion, but you can never hit 100 miles an hour. That's bizarre. Now, it doesn't seem that bizarre to us because it's so big. And Planck's constant doesn't seem too bizarre to us because it's so small. But this stuff is weird, You're telling me that there's the smallest something? Like, there's nothing smaller than that. Like, everything is made up of multiples of this something. Planck didn't fully realize this, nor could he absorb what these ideas really meant. Planck's discovery raised more questions than answered, and he certainly didn't set the world of physics on fire. So obviously, nobody's jumping at this, because here you're trying to explain an unexplained phenomenon, and you come up with another unexplained phenomenon that occurs nowhere else. Nowhere else are they seeing anything that will even make this make sense in the real world. He had clearly worked backwards and discovered a process not seen anywhere else in nature. Most physicists regard this as a mathematical trick and a device used to just get rid of the ultraviolet catastrophe. Another weird trick. Dude, it's a trick, In a letter to Robert William Wood in 1931, so this is in his memoirs, he wrote, "I can characterize the whole procedure as an act of despair. A theoretical interpretation had to be found at any price, however high it may be." Also, physicists were very busy in 1900. This is when they were discovering X-rays. This is when they were discovering atomic radiation. All the stuff was going on. And you solving a really hard problem using a little trick wasn't exactly the top of their list. But luckily, he was very highly respected. He still did a lot of prominent work. And he was so respected that they patted him on the back, put it on the shelf. You know. We're not going to discredit you and, run you out of town, but try again, So if they made the time to read his papers, they were merely intrigued at the mathematical trickery. So most scientists weren't paying attention, but if they were paying attention, this isn't any breakthrough knowledge. It wasn't like, oh my gosh, you're on to something, But there's Einstein. Now, everyone knows Einstein's the man. Or you don't know. We already discussed. Einstein's like a bird, The cool thing about Einstein, and I know there's a lot of myths about him, but the biggest is like, he wasn't very good at math. You ever heard that? He wasn't very good at school. Which is actually true. He wasn't a straight A student. He was not valedictorian. He actually was a clown. He was a ladies' man. Einstein had game, He's an experienced violinist. He would go to the bars or the pubs, the coffee houses, and he'd play a violin and, woo a hot chick to his room, I mean, obviously, he was not of the established core, These scientists were all top hat, cane. Einstein, I mean, this is the best you've ever seen his hair. Like, he never combed his hair. Like, that to us is pretty cool, Now we see someone that does comb their hair, like, oh, they're bohemian, This was back in 1900. Like, people comb their hair. If you didn't comb your hair, something's wrong with you. Like, you're just a little bit off, And actually, after he finished his master's degree, he couldn't get caught on. Like, all his teachers, professors, nobody took him seriously because he was a clown. He wasn't all 100% in his studies. He could not get work anywhere. Because as many of you know, to get a PhD, you have to actually be adopted, accepted, and mentored by an established scientist. Nobody wanted to mentor him. He had to go all the way to Switzerland to find someone to look after him, And as many of you know, that's where he got a job, becoming a Swiss patent clerk. So here was his patent clerk. And Einstein later said being a patent clerk to him was like the best thing could have ever happened to him. Because think about a patent. Everyone's sending you all their ideas, written on way too much paper. Your job as a patent clerk, A, is to decide what's crap and what's not crap. Yeah. And not just what's already been decided, what hasn't been decided. But you have to boil down somebody's 25-page proposal into one simple idea. And is that idea already established? Because Durand could have had a patent for a machine that has nothing to do with your machine, but his key idea is already protected. Right. Your thing is something totally different. His is a gumball machine. Yours is a racehorse track. That's a leap. But somewhere in there, that idea is covered by the gumball machine. And this is actually what the key of the heart of science is. Boiling things down to their nitty-gritty necessity, And so it was as a patent clerk, as many of you know, and he wasn't even a doctor. So he had not received his PhD. He was just Albert Einstein, not Dr. Einstein. He published in 1 year 4 papers. Now, this is known as the Year of Miracles, the Annulus Mirabilis. Because in order to get a PhD, you have to publish a paper, right? You have to publish a paper that actually added something to science. You have to discover something. You can't just you can't call yourself a doctor in the scientific world and all you did is memorize the textbooks. Like, you need to discover something new. So if you publish a paper, you become a doctor. If you publish a really good paper, then you get a really good job, you get tenure at the university. Now, if you publish a groundbreaking paper, then you're like the man. Those are people like Lord Kelvin and this and that. Einstein, who was nobody, rejected by his schools, had to go to Switzerland. He published 4 groundbreaking, earth-shattering papers all in the same year by nobody. Nobody knew who he was. First paper, because it ties into what we did, was called Brownian motion. How many heard Brownian motion? No one's heard of that. It's random. Brownian motion was a century earlier. Now we're going back to 1800. There was a botanist, famous botanist, I don't know, Thomas Browning. I forgot his name. Who cares? He was a British botanist, and he studied plants. And as you can know, he studied chlorophyll, and he was actually botanists slash biologists is what they were in that day. So they were breaking down the cells and looking under microscopes. He noticed something really odd. Under a microscope, one day, it just so happened, he had a drop of water on the slide and a tiny microscopic piece of pollen. Now, you know plants, pollen, like those fine dust.
Yeah.
One dust of pollen fell on the drop of water. And he's looking at this under the microscope. And he noticed something really weird. This little tiny piece of pollen, which is now blown up, it's moving. Weird. Being kicked around. It's called Brownian motion.
Yeah.
He had no conception what was going on. But he published it, remarked it. Now, any physicist in their right mind probably wouldn't even know about this. Einstein apparently paid attention in history class, you know? Because remember, at 1905, still, atoms weren't accepted. They were still like, EBGBs. Einstein's like, look, here's the Brownian motion. Then he grabbed the Boltzmann statistical mechanics, did the mathematics, and he showed exactly what's happening. The water molecules in that drop of water are bouncing all over in that little drop of water. The grain of pollen is so small enough that it's affected by the molecules of water. The statistical mechanics, the chemists have been saying forever, look, this is what's happening. Physicists are like, no, it's not happening. Einstein gave him a visual representation of atoms obeying these mathematical rules that show miracles are possible. And from that, he could model how it was moving and why it was moving that way. So he basically cemented once and for all, atoms are for real. And it was because of this paper that from then on, nobody could doubt the existence of atoms. Because the math was there, the visual was there, all of it makes sense. And here you see that, again, the genius of Einstein is it's not that he even came up with stuff, you know? Now, Einstein came up with a lot of stuff, but there's a lot of Einstein haters out there, which really annoy me. Like, oh, he didn't actually come up with those ideas. Like, dude, really? All discovery is like almost there, you know? It's like he was able to pull two seemingly abstract things together and formulate it, you know? Oh, how many heard of this? This was his second paper. E squared equals m squared c to the cube plus p squared c squared. Now, P stands for momentum. That's your movement. So if something's not moving, your momentum is what? 0. 0 squared is what? 0. And 0 times c squared is 0. So if you have no momentum, you get this. And you all remember in algebra, the squares, you can simplify them into E equals mc squared. That's how we all know and love it, you know. Now, anyone know what this means besides you and you? TJ? Huh? No? Do you know what any of the letters mean? I know, but what does E stand for? Eggs? Oh, electromotive force? All right, John, what do you think?
Energy equals mass times the speed of light squared.
Yes.
I think it was
So-
energy. That's all I knew.
So C is speed of light, E is energy,
Mr. Isaac Newton?
and M is mass. Yeah, we had that in the. No, we didn't have that in my Newton equation. Now this is huge. Now, even if you know what it is, I always knew what it was, but I'm like, what's the big deal? Like, I get it. Like, but think of it this way: if you just solve for M, think of it this way: mass. Now, mass. We all know what mass is. Mass is like us. We discussed mass and weight, but now we say mass is actually the energy of you divided by the speed of light squared. Again, we have it inversely proportional to, you know, something squared. Gravitational was radius squared. Then we had the charges, radius squared. Now we have c squared. This was breathtaking stuff. Now we're going to go into relativity later, but that's his second paper. The third paper, and this is actually what he won. Well, the third paper, we'll say really quickly, was his theory of relativity. Well, people forget there were two separate papers. The first one was the theory of special relativity. And then 10 years later, he published the theory of general relativity, which was like the super, super triumph of all science, you know. Special relativity was, basically it states this. It states a lot of things. But the coolest thing is that time is relative. Now again, that's totally weird. Like, time is time, right? A second is a second. Like, what do you mean second? Like, in China, a second is slower? Like, what are you trying to say? Well, it's all relative to how fast you are moving relative to something else. So my wife is a twin, Lachey. She was here. She's not here because it's Dominic's birthday on Monday and there's on her birthday. If you took my wife's twin, put her in a space capsule, and shot her off on a rocket at near the speed of light, you can't go the speed of light. You just go near the speed of light, all right? We're going to go 99% the speed of light. And she goes that for a year, right? A light year. She realizes a light year you're not getting anywhere. So you should probably come home. So she turns around and comes home, right? My wife and her sisters, they're 28. So she comes back, she's 30. Ashley, my wife, her twin, instead of 28 to 30, she will be 78 years old. She would have aged 50 years, where her sister would have aged 2 years. That is crazy. Now, part of the reason why Albert Einstein didn't win the Nobel Prize for this is because it's hard to prove, especially in 1905. It took a while. I mean, he was so far ahead of his time, you know. Now, the closest we can do to this is we have proven this experimentally, but we've done the atomic clocks. So what we do is we get 2 atomic clocks, which are accurate within a trillionth of a second, right? And so they're never going to go off. They're so accurate. They're exactly in tune. And they take one, put it in a Black Hawk. The Black Hawk go like Mach 7 or whatever. It can go from San Francisco to LA in 1 hour. That's how fast it is.
Yeah.
All right? So you fly it, and then you fly it back, right? Kind of like a little mini light year trip. When they do that, what do they find? The clock on the Black Hawk is younger than the clock that didn't move on the ground.
Right.
Now, it's younger by like a billionth of a second because you're not going nearly the speed of light. But the time dilation effect happened. Length varies. Depending on what speed you're going, 1 foot is not 1 foot. If you're going near the speed of light, 1 foot could be this much. It could be this much, you know. All this weird stuff happens. We'll get into that later. Just wanted to mention it, you know. The fourth paper deals with what we've been talking about this class, and that's called the photoelectric effect. And that's actually what he won the Nobel Prize for. Because they were like, okay, we can prove this. You know? All your other stuff, it's going to take a while, you know. The photoelectric effect stated this, and scientists were just so baffled. Like, this was the most bizarre thing. If you took light, right, and shined different types of light on different types of metals, electrons would shoot off.
Yeah.
Now, this makes sense to us. Remember, a wave of light has energy, right? So if you give an electron enough energy, it will eject. You know, electrons orbit we haven't gone over this yet, but you know the electrons orbit the nucleus. You know, they're happy there. But if you give them enough energy, they'll shoot off. They're like, oh, I'm free, you know, and they bounce off. So they knew you put energy in, electron shoots out. Here's the problem. Let's take a lamp of red light, right? We're shining it on a piece of metal. We can measure the electrons shooting off. They're shooting off at 100 per second, and they're hitting me at 5 meters per second. Whatever, you know. Now we're going to increase the intensity, right? We're going to increase the intensity so we're shooting more energy into those electrons. Now, in this experiment, to increase the intensity, what do? You take the lamp and you move it closer, okay? So now we're doing much more intense light. So what they expected was more electrons shooting off, and they'd be shooting off at higher velocities. If you give an electron more energy, it's not going to hit you at 5 meters per second. It's going to hit you at 10 meters, 15. I don't know. Give it more energy, it's going to go faster. This is classical mechanics, right? It's not what they found. What they found was when you increase the intensity, the ejection rate of the electrons did increase. So instead of 100 per second, it was like 500 per second, whatever. But their velocities all stayed the same.
Right.
They were all still moving at 5 meters per second. Even though you're giving them more energy, more potent energy, all 5 meters per second. Okay, this is weird. So if you encounter something weird, you're going to mix it up. So you know what? Let's put a filter on the light. Let's make it red light. Oh no, it is red light. Let's make it blue. We're going to make a blue light. All right? Same experiment. Now the blue light, the electrons now, instead of 5 meters per second, they're moving at 25. Why? I have no idea. Why is the blue light, it's a shorter frequency, okay, more speed. Again, if you increase the intensity of it, same thing. More electrons shoot out, but they all have the same rate. The more the test they did with the lights, they saw that not only did their velocities didn't change, but there were certain caps where the electron rate would increase as you increase the intensity, but eventually it wouldn't.
Yeah.
There were some lights in the rainbow that electrons wouldn't eject at all. So you got 5 per second, 8 per second, you get to yellow light, none. We're protesting. We're not moving. We don't like yellow. Yellow means slow down. And then we go up into blue. Oh, we're going faster. Once you got into the ultraviolet, it was really fast, you know. But eventually, you reach a frequency ultraviolet light that it wouldn't increase at all. It was just, there was a cap. No idea what this meant. Einstein, being the genius that Einstein was. Now remember, at this point, light was now proven a wave, not just for 100 years, but it's proven mathematically. Like, this is math, people. Like, this is real as a real as a real. Einstein's like, you know what? Light's not a wave. It's a photon. It's a piece of matter. And Planck, that dude that nobody was paying attention to, I think he's onto something, you know? This constant is actually, and I glossed over it because what Planck found was that energy is equal to Planck's constant times, it's so retarded. It's a V, but it's actually the Greek letter nu. That's why science gets so retarded with fonts. You cannot use different fonts. You have to use Times New Roman, or else science papers mean nothing. Because if your V has a little lip at the end, it's not a V. It's the Greek letter nu. You know, they have a whole bunch of, like a W. But if it's curvy, it's not a W. It's omega. You know. Anyways, he said he saw in this equation that energy equals Planck's constant multiplied by the frequency. Einstein's like, oh, this is what I'm seeing here. The energy is equal to the frequency of the light multiplied times equals, did I write it? Oh, you know, I didn't write it down. See, that's why I need to write stuff down. But basically, the equation said that there's a light, and the reason why you're seeing this weird effects because it has nothing to do with intensity of the light. It has to do with the wavelength of light. Because each wavelength of light, if you multiply it times h, a wavelength is a wavelength. It doesn't matter how strong it is. When you multiply it times h, that's how much energy it is. So you're sending a packet, photon, a packet of energy, and that's what allows it to shoot off. And that's why the intensity doesn't matter, but the ejection rate does matter. And then he also explained why certain colors, and he gets really technical, but the whole principle is, and here's the curve, and this curve actually forms Planck's constant. So now Planck goes from, nobody knows what you're talking about, this doesn't really happen in nature. Einstein's like, you know what, light is now not a wave, it's a particle. Not only is it a particle, but this Planck guy actually was onto something. Planck's constant is real, you know, and light, photons have exactly the energy of Planck's constant times the frequency. Really, again, very simple, elegant equation. And actually, Einstein didn't even realize it at first, but this actually proved his own equations. If you solve his equations for P, momentum, instead of like momentum's moving, the energy rate, again, it gets all ugly with the math, and I don't want to put it up there, but it basically proves his E equals mc squared, or E squared equals m squared c cubed, blah, 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 blah. So now scientists are really confused. Because now not only are they having to deal with the fact that energy really is cut up into little tiny chunks, but now you're telling them light, two different things. Alive and dead, on and off. How can light be a particle, but it's also a wave? So just in case you know, particles don't go through stuff, right? Yeah. So a photon can never go through this wall. But a wave, now light can't, but your cell phone, that's a higher frequency. That wave goes right through the wall, you know? Or glass. Glass is solid. Photon won't go through glass, but a wave will. Light, You could run 1,000 different tests, and whatever you test it to be is what it is. So if you devise a test to prove that light's a photon, you'll get a result that it's a photon. If you run tests to say light's a wave, light's going to be a wave. So you're seeing a physical manifestation. And us, in our brains, we all know that light's a wave. We may not know intuitively light's a photon. The easiest that is fiber optics. I don't know if you know what fiber optics are, but these little pulses of light, the little photons that go through big, long pieces of glass. And that's how all our telecommunications and wires and blah, 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 Here's Albert Einstein's quote. There are therefore now two theories of light, both indispensable without any logical connection. So Einstein was giving birth to quantum mechanics, didn't even realize it. But remember, he's not tripping because he's Einstein. So he's like, look, it is what it is. J.J. Thomson, which was a world famous, he won the Nobel Prize in 1905 for proving that the electron was a particle. 30 years later, his son, J.T. Thomson, I believe, won a Nobel Prize for proving that an electron was a wave. Two different things, And we're going to keep running into this. And again, we have to reconcile. On and off. Alive and dead. Oh, shoot. Hold on. Is that it? I got one more slide. That's it? That's the end? That's the end! So now we have our opening. The stage is set to now investigate how things can be one thing and another thing, And again, if you ask most scientists, like I asked my physics teacher, so they don't know what light is, He's just like, no, scientists don't know what light is. But she's lying, Well, he's lying, but he's not lying. Because we don't know, now you know, Apparently, Biggie Smalls was a philosopher. You don't know, now you know. Never mind, that was a stretch, But starting next week, we will go into the breakdown of the atom and how all this starts coming into play. And that's when we start seeing a lot of weird stuff. And we'll start seeing some really cool experiments that break down these principles. But here you have one thing, another thing. Any questions? Yes, sir.
What was the third paper that Einstein wrote?
What was the what?
The third paper that Einstein wrote?
Okay, he had the Brownian motion, which is the atoms. He had the photoelectric effect, which is what I covered. He had the E equals mc squared, the energy mass equivalence paper. And then he had the theory of special relativity. Those were the four. And that's what made him famous. He was the first famous scientist. No scientist had ever been famous. Einstein was a freaking celebrity. You look at, I was watching newsreels, and he's on a cruise ship, and everyone in America, everyone was just like, nobody understood what he did. It's like Stephen Hawking. We all know he's a genius, right? The black hole. Any of you tell me what he does? All we know is he's really smart. Maybe you could tell me he wrote a book called A Brief History of Time. It's a really hard read. And he's in a wheelchair. Now they're making a movie about him. I don't know if you saw. It looks pretty cool. Making a movie about his life and all the struggle. And they're trying to romanticize it. Dude, he's been through 4 wives. But in this movie, he's had one wife. A very long time. No, he gave about 15 years a pop each wife. So, it was a decent time, But Stephen Hawking is pretty amazing, but not on the level of Einstein, Historically, there's Einstein, there's Newton, and then there's Maxwell Faraday. They're like a 2-part Einstein. Because Einstein was like Faraday, creative, think outside the box. But unlike Faraday, he's also a mathematical genius, Even though he actually wasn't that good at math. I mean, he was good. He was just at a low genius level.
Yeah.
That's why a lot of his papers were like the Einstein-Rosen bridge, or Einstein-Polanski-Rosen bridge. He had lesser people do all the long division.
Lesser people.
Because relativistic math is stupid, It's insulting. It's insulting how difficult it is, And that's another reason why people don't understand geniuses, because if you did, you'd be a genius. So it's that's why I'm trying to take really complex things and just trying to make them understandable, without flashing a bunch of crazy equations. So next week we'll continue. Hope you enjoyed yourself. All right, and I actually hit record. Let's see.
We didn't record last week.
No, well, I'm going to record it